So number 19, and that's a favorite antiderivative. This is x to the power of -3. Power rule for antiderivatives. I guess after all we went through, this type of integration is so extremely nice. And we put the 1 to b and a limit b approaches to infinity to make it look perfect. So we're gonna go with x to the power of -3 plus 1 is -2. And I also divide this by -2. That's antiderivative. So go from 1 to b, 1 substitute, and then take limit after we're done with the substitution. So this is actually 2 in denominator and x squared in denominator. So x squared will turn into b squared. And then we're gonna subtract from this the analogous value but at point 1. So it'll be 1/2 times 1 squared, right? And then I take limit of this, see what happens. And actually, you can take limit at this stage when b is approaching to infinity. So that first fraction is going to disappear, turn into 0. Right? B squared approaches to infinity, and 1/infinity is going to 0. So we end up with positive, 2 minuses plus, and 1/2 is our result, and they like to say it converge. Okay. So some people said converge, some people gave 1/2, and that was fine either way. So I'm glad that you got used to this infinity structure. And today I'd like to just move on because there is really not much in this section, just to see what's in the next chapter, because we're done finally with chapter 8, and now we're gonna take a look at chapter 9. That's the plan. So in chapter 9, we're gonna deal with very different material, which I think is a little bit more pleasant as problems are more compact. So they're talking about sequences of numbers. And when they talk about sequence, it means it's infinite. So ... means we have infinitely many terms. So what they do is they produce names for each term. First term, a index 1, then second term, third, and so forth. And then if I can describe so-called nth term, then I can describe the way this sequence looks like. So they given us various examples of sequences. Sometimes people say infinite sequences, but when we use word sequence, we assume it's infinite. So they have various examples of sequences, and they trying to produce formula for the nth term. So you can describe the sequence, how it looks like. For example, if you have a formula for the nth term here in whatever format, then all you need is to carefully put down the first term. So they call it as a index 1. And for that, we use power of 1. The next term will be a index 2. That's going to be with the second power. And then third term, fourth term. And when they start to simplify, they notice that this sequence is actually 2, 4, 2, 4, 2, 4. So technically, a sequence could be just about anything, but they notice that to produce 2, they want to subtract 1 from 3, and then to produce 4, they want to add. And that's why they decided to have odd powers of 1 when they subtract and even powers when they add. So that's an interesting way to give a description of sequence of 2s and 4s. So we'll see various ways to describe sequences, like in the part C here, they have a sequence that is described by that formula for the nth term. And again, all I need is to see what happens when n is 1. So it looks like they have it for the first place and simplifying, get 1. Then what if n is 2? So it looks like 4/3, and then 9/7, and etc. and etc. And well, using the formula, you can always uncover the actual terms. So let me do some exercises here at the end, just to practice dealing with the sequences. So section 9.1, they're talking about producing a few terms of the sequence, first 5. So how about exercise number 3 that says, look at the formula for the nth term, which is -1/4 to the power of n. And then write down first 5 terms. So that'd be A1, A2, 3, 4, and 5. And then you just need to replace the n with this index. So 1/4 to the power of 1, 1/4 to the power of 2, and etc. And sometimes when you start to write these terms, you don't really need to use the formula. You can intuitively see what the next terms are coming out. So that's a 1/16. The next will now change sign and it'll be -1/4 cubed, or 64. And then you can get +1/, and then multiply this again by 4. So looks like it's 256. And then another term with a minus sign. So when I multiply 250 by 4, it's 1024. So you can get these terms sometimes when you get intuition of what is going on without actually using the formula. So you just start to see what to do with the previous term to get the next. So of course, when you're given the formula, that's perfect. What if you don't have the formula? Well, then you need to produce one. So let's say exercise number 23. I need to observe these terms and see how I could move from first to the next and etc. And looks like I can just add number 3, right? To get from 2 to 5 to 5. I need to add 3 and see if this is going to work when I move from 5 to 8. And looks like it does, right? So if I keep adding 3, then I'm going to get the formula for the nth term. So for the first term, I can say it's number 2. Then for the second term, which is 5, I can think of 2 plus 3 times 1. For the third term, which is 8, I add again 2, but with 3 times 2. So what about the nth term? It looks like how to start with a 2 and add 3 one less time, so it's n minus 1. And of course, you can simplify this and get the nth term formula in a nicer simplified form, right? So it's a good idea to be able to get the formula for the nth term, but it is not very obvious as in this particular problem. So sometimes it is not that straightforward. So main thing is to observe and notice what you do to produce from first term the second term, and then if that works for the third, and if it does, then you got the idea of the formula. So what else is here? Well, they trying to find a limit of the sequences. So for example, in exercise 35, we see where the terms of the sequence will approach to. Like, for example, when I look at exercise number 3, I notice that my terms are jumping around 0. So first term is -1/4, and the next term will be a +1/16. So it's like 4 times closer to 0, but on the other side of it. And then next term will be -1/64. So that's again 4 times closer to 0 than 1/16 is. And then I get the next term, which is even closer than that. And then again, even closer. So looks like this approaches to 0. And that's a geometric way of doing it. But when I look at the algebraic way, if I take the limit of 1/4 to the power of n, well, 4 to the power of n goes to infinity. So 1/big is small. So indeed, this goes to 0. So all we care about is just taking the limit of this nth term. So it's nice to have the nth term in this case done. And when I take a limit of this particular exercise, looks like it's going to be 5, right? The reason it's 5, you can take and use L'Hopital's rule, or you can see that if you divide it by n squared, the top and the bottom, you will get to 5. That's what we did in calculus 1, right? So if I divide it by n squared, the top will get a 5, and the bottom will be a 1 plus 2/n squared. And that way we get 5/1, because that 2/n disappears, it turns into 0. And that's why we're always trying to divide by the largest power or by the smallest power. In this case, it actually doesn't matter what power, largest or smallest, because they're the same. And we get the limit. So nth term approaches to 5. So you can do problem like 29. That's a little bit different one, just to recall what factorials stand for. So if you divide 11 with this factorial by 8 with factorial, then you don't scream out loud 11. No, it's 11 times 10. So it's a product of these all the way down to 1. And there is 8 also appearing here. And with 8 factorial, we start with 8 and we go down all the way to 1. And this enables us to cancel, right? Enables us to cancel and get just the product of 11 by 10 and by 8, and you can even calculate this, 88 and a 0, right? 880. So they say simplify. So you can just notice that something is going to cancel. So it turns out this type of exercises is a preparation for the future. So you can try another ones in this little group of problems, and that'd be an interesting thing to do, I guess. So let's see what else. It looks like problems here indeed are pretty compact, right? And I'm sure this is gonna make lots of people feel good. Oh, what happened to the 9? Yeah, I put 8 instead of it. How could I? That's absolutely correct. It's not gonna be 880, but 990, right? Thank you. I simply replaced it with 8 for some reason, and I have no idea why. So that's 99 with a 0. Thank you for checking this out. That's very good that you're paying attention. So looks like the next groups of exercises are talking about convergence or divergence of the sequence. So what are they really talking about? Well, if we find a limit, then we say the sequence is convergent. And if limit is infinity, or there is no limit, then sequence is not convergent, which is divergent. When you say, Alex, is it possible there is no limit? Yes, anything is possible. Remember, we had sequence 2, 4, 2, 4, 2, 4, ... So what does it converge to? Number 2 or number 4? Because it just keeps jumping from 2 to 4, and so 2 and then 4, and again 2 and again 4, and again 2 and again 4, again 2 and again 4. When Alex may be enough, there is no limit. So we have the algebraic definition of limits, that epsilon delta. So if you, that's for limits of functions. So you can say for sequence, whenever you take a little neighborhood called delta, then all following terms might have to fall into it. So if I take a neighborhood of 2, say from 1, 9 to 2, 9, then all the terms must fall into this neighborhood starting at some place, and we always going to have 4, so it's not going to be in the neighborhood, it's not going to be in this region, so we say there's no limit. So that's the idea of the limits when you do them algebraically. So all terms must fall into some very, very small region around this limit, and that's what I guess they trying to show on the picture here on the left side in part C about exercise number 15. So what they do is they trying to produce a function, because I'm sure you like limits of functions, that says once I get more and more terms, looks like they all start to approach to level of 0, because y coordinates is what I care about, and they seem to get lower and lower. So for each point here, I get that y coordinate, that y coordinate, that y coordinate, and so forth. So they actually turn to 0, and that's why the limit of the sequence is 0. Intuitively, with a picture, so we got intuition. But we don't have to always graph it. You could just find limits using our methods of finding limits. We had already so many methods, right? The L'Hopital's rule or the other algebraic methods. So any way is fine. And that's what they're talking about in here. And sometimes you may need to do a little bit of work to prepare yourself. So let's say, how about exercise 57? Find the limit of that stuff. Well, probably the L'Hopital's rule is going to be a way to go in exercise 57, because all they want is find limits when n approaches to infinity. So they could have put word limit and n approaches to infinity, but for some reason they decided not to do that. They decided you to put that limit. They just asked you to find it. So notice that since infinity over infinity is what we have here, notice that ln approaches to infinity, right? Even though it does it very slowly, but it keeps going up farther and farther. So eventually it reaches any level. So it is going to infinity on the top and definitely on the bottom. And since this is the case, well, take derivatives. So it looks like we're using the stuff from previous chapter now and see what will come out. And we might need to take a derivative again, but it's fun. We know how to take those derivatives. So denominator is 2. And what about numerator? Well, ln, derivative of it is 1 over, and 1 over whatever's the logarithm is taken off, that's n cubed. And then I times this by the chain rule. I need to multiply it by derivative of this n cubed, which is 3n squared. And looks like now we can either differentiate it again or cancel that n squared, so that we have to differentiate it too many times and end up with 3 on the top and then 2 over n on the bottom, right? And then you can take the limit right away. It's 3 over big, which is small. So the limit when n approaches to infinity is equal to 0. So again, we already had so many ways to deal with limits that I'm sure this is something that you're gonna enjoy. So in the next section, we get to work more with those sequences. And in the next group of exercises, they actually want us, looks like, produce the formula for the nth term, which might sometimes take a little bit of a time, because sometimes it's not that obvious what we're doing from term to term to get to the next ones. Say, how about if I think of number 80, exercise number 80. Well, I guess you just need to be creative. I am not planning to ask you this type of questions for the exams, because sometimes people get stuck as might get panicked or whatever. But if you just think of it over weekend, I'm sure it is interesting. So 1 plus 1 over 2. Well, so I need to relate that 2 in denominator with the index, because the next term, a2, they say is 1 plus 3 over 4. So again, I need to relate that second term with the index. So what happens with the top and the bottom? Well, looks like I add number 2 to the top as well as to the bottom. Do I, or something else is happening? Well, look at the next term, and then you're probably gonna better see what happens, because now I can see that looks like since I have 8 here, then we actually, and that's a 7, dealing with powers of 2, right? So it's like 2 to the power of 1. This is 2 squared. and this is 2 cube. And then what's on the top is going to be 1 less. So that's a 2 cube minus 1. And this is going to be 2 squared minus 1. So looks like I got an idea of the nth term. So 1 is still here. And I need some power of 2. It looks like it's the same as the index. So it'll be to the power of n. And numerator is 1 less. So you produce formula for the nth term, and that's all they wanted. If you want to simplify this, you can also find the same denominator, simplify, again, if you want to. It is up to you, but I guess algebra is not that much of a concern here. The concern is to get the actual nth term. So those are interesting formula. And let me try one more and then see what else is here. So I think that those are not very standard exercises, right? And again, don't worry, don't panic. I'm not intent to ask you this on the exams. I just think that in general, it's worth to take a look at them, and then maybe you're gonna like this. If you look at 85, the numbers increase so tremendously that it's kind of hard to say what's happening with them. So maybe one just needs to tackle these with calculator and see what really is going on, because some problems you might get stuck with. But I'm sure after half an hour playing with this, you will come up with something if you're really persistent enough. If you see how you get from 2 to 24, and then is that the same way to get to 720? Maybe factorial is being used here, who knows? Or maybe something else, some power in factorial, or their combination of some type. So there's always various interesting observations. And I guess I'm not gonna get much into this because it might be a little bit way too time consuming. So I think 85 and 86, they have to do something with factorial. It could be 2n factorial or 3n factorial or something like that. And that's why these terms increase so quickly. And now I want to show you one interesting theoretical idea about so-called monotonic sequences. So sequence could be shown with points. Notice that all points correspond to the whole numbers, 1, 2, 3, 4, 5. So it just helps me to see where each term is. 6 term is someplace here. But what we really need is their y coordinates. So 6th term is going to be pretty much same as 0. So it looks like 7th term is also even closer to 0. So it looks like this whole sequence, they like to put braces instead of writing the word sequence, is approaching to 0. And it's also going to be called monotonic. Monotonic means that terms are just behaving in monotone order. So they just keep getting smaller, 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 or larger, larger, larger. So they don't start to change, smaller, larger, smaller, larger. So this one is not monotonic, not monotonic. But it's also approaching, looks like, to level of 0. But this one is monotonic. So here's the very useful statement from analysis that says if sequence is monotonic and also bounded, because there might be monotonic but not bounded, it may be bigger, 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 and there is no bound. No matter what bound you imagine, eventually it'll cross it. But here's boundary. So it cannot cross it. So it keeps on increasing, but does not cross the boundary. Then people say there's going to be a limit. It doesn't have to be L, because one can say the boundary could be also this one. It may have some other limit, but as long as it's bounded and monotonic, then there is a finite limit. So word converges stands for finite limit. And you can see there is an interesting proof by contradiction that they actually came up with. And I'm not going to go over it because it uses epsilon and delta, but if someone is interested, you can try to look at it over the weekend at that proof. And if something needs to be clarified, I'll be more than happy to do this, because I guess this is, well, a little bit beyond the scope of the calculus class to do all of these proofs, especially. I know that some people never saw that epsilon delta story, so that may be a little bit overwhelming. But if somebody already saw it and likes it, I think it'd be very interesting to actually understand how they produce this proof by contradiction. So that's something what people do. So they say, what if sequence is monotonic and bounded, but it is not convergent? So, and if you see that, if you say it's not convergent, then to actually do the proof, you show that it is going to be either not bounded or not monotonic or neither of those. And actually they go with monotonic, but they show that if it's not convergent, then it is not bounded. And that's like A, then B, which is in logic equivalent to not B, then not A, which is a contrapositive argument. So it turns out this one is equivalent to that one. So these two statements are actually equivalent. And that's the key idea behind this little proof. So if somebody will decide to read it, and we can definitely work it out next time if you want. But again, we don't have to. So monotonic and bounded sequences. And I guess that's pretty much all this little section contains. So as long as you have the formula for the nth term, then everything is nice. You can describe it. So maybe I can try one exercise with science, because that's something a little bit different, right? So let us try something like, for example, 95 sine or cosine. It turns out that when you have the sine function, so if an is sine of n times pi, turns out that the term's actually going to be repeating pretty much in all of the cases if you have pi involved. Because if you write down what your first term is, then it's going to be just a sine of pi over 6. And the second term will be a sine of 2 pi over 6. And 2 pi over 6 is just pi over 3. Well, let me write it 2 pi over 6. I think that'd be better visible. Then next term is 3 pi over 6. And so forth. But the point of story that eventually, because you'll be running around the circle with the angle pi divided by 6. So you will have 12 points to run around. So after the 12th step, you're going to start repeating the same story over and over again. So sine of pi over 6 is going to be 1/2, right? This is a radical 3 over 2. Then we get a sine of pi over 2, which is 1. Then we get, again, radical 3 over 2, right? Let's say 4. So they wondering, is this monotonic sequence? And the answer is, looks like it's not, because you start to increase your terms up to 1 from 1/2, then you decrease your terms, right? Actually, sine is 1, so A7 will be a sine of this angle, which is 0, and then you get to negatives, and then you start to, so basically, what is the sine? It's a y-coordinate of each point, right? So y-coordinates are going to be just running around in between -1 and +1. So they're just going to keep on running around. So it is not a monotonic sequence, even though you just keep repeating again and again the same cycle of numbers, but it is not going to be convergent. It just keeps on running, like we already had example 2, 4, 2, 4, and there would be 0, 1/2, radical 3 over 2, 1, and then again 0, 1/2. So it just runs around with this same values. So since it's not monotonic, even though it's bounded, because sine is always in between -1 and +1, but it is not convergent. So anyways, it's a little bit tedious, right? But one needs to get a piece of paper and pen and to actually write down a few of those terms. So maybe you can do one for a quiz, actually exercise 1 for the quiz. So write first 5 terms of this sequence. I'm sure you're going to like this. So please don't hurry. After the quiz, you can log out and have a great weekend.